Energy notes. No frills, no jokes, one take, one win. Let's go. Do you feel the So we're going to start with energy. We got the work energy theorem. Work energy theorem states that the work done is equal to the change in kinetic energy of a system, and that the work is equal to the force applied dot x, and that is Fx cosine of theta. Do remember that if the force changes with x, you have to integrate, so integral f dot dx, which would then be the integral of fx cosine, or f dx cosine theta. So f cosine theta dx. And remember that the cosine of theta can change with x depending on whether your force is path dependent or path independent. Also remember that the change in kinetic energy is equal to minus the change in potential energy, and that can also be due to energy loss. All right, so that's the work energy theorem. Now we got to talk about power. Remember that power is equal to the amount of work done over time. So this would be equal to the change in kinetic energy over time. This is when, some kind of engine or something like that will give you some kind of power output. We know that the power times the time is equal to the work done by that engine. All right. Now, fundamental theories of energy show us that, if we integrate the acceleration, right, in order to find kinetic energy, we'll get that energy from kinetics is 1/2 mv squared. Then we can also find the energy from gravitation, which is a potential energy, right? That potential energy will be mgh, which is just the force times the change in height. So really this is mg delta h. And then we get that the energy due to a spring will be also a potential energy, us, which will be 1/2 kx squared. Or if you have a nonlinear spring, it can be anything as long as it's the integral of the spring force with respect to x. Keep in mind that this is path dependent. We know that the spring force, let's say, would be minus kx for a linear spring, and so that gives us 1/2 kx squared, and it would be negative. So that would be the work done, and if we recall, the work is equal to minus the potential. So that means that the potential energy from a spring is 1/2 kx squared. Now, if it's a nonlinear spring, it could be kx cubed, could be kx, 1/3 kx cubed, 1/4 kx to the 4th, something like that. But for the most part, this is what we're talking about. Okay. Now, how do we use this? Well, if we've got something going from up a hill to down a hill, notice that this is not perfectly flat, so using forces is kind of out. Let me make sure that my mic... All right, so we've got this object going down this hill. Like we said, the hill is not flat, so this is not an inclined plane. This is some other kind of shenanigans. I'll state what kind of energy I have at the beginning, what kind of energy I have at the end, and if all my forces are conservative, then they will be equal. So at the beginning, I have gravitational potential energy. At the end, I have kinetic energy. And if the only force acting on this is gravity, aka the coefficient of friction here is 0, then energy is conserved. So mgh equals 1/2 mv squared. I can cancel out the m's and get that v is equal to square root 2gh at the bottom of the hill. Good. Now, if I wanted to say, hey, I have this same kind of a problem where I've got a thing going down a hill and then it's going to crunch a spring. You know, let's assume that this collision is elastic. That just means that energy is conserved. We're going to talk more about when energy isn't conserved in our next unit, which is momentum. So, you know, there's that. So at the beginning, all we have is gravitational potential, and at the end, after the spring is compressed, all we have is spring potential. So that means I can set my potential energy at the beginning, mgh, equal to my potential energy at the end, 1/2 kx squared, as long as there are no non-conservative forces. So again, mu here has to be 0, ergo I have no friction. And then here I can find how far the spring would compress. I get mgh equals 1/2 kx squared. I can get 2 mgh over k is equal to x squared, so I would square root this, and I get that as my final answer. X is the square root of 2 mgh over k. This is a heck of a lot easier than figuring out all of these problems with forces, which is why we're using this to solve them, right? So now let's talk about energy loss. So energy loss, or add. So when energy is added to a system, that means that your change in work is positive. So that means that you have, you know, added something to your kinetic energy. We know that the work done is equal to the change in kinetic energy. So if I say that I have a person, you know, pushing on a box, or pulling a box, let's say, because it looks more like he's pulling. So we have a person pulling a box with force, let's say 50 newtons. Let's call this box 20 kilograms, which is like 40 pounds, which is a lot. So now we can figure out the work done by this person if this box moves at a constant speed. Right? So that means that there's some friction force. So if this box is moving at a constant speed, and let's say this person pulls it for 5 meters, right? So we know that this person is going to pull this box for a distance of 5 meters at 50 newtons. So how much work does the person do? Well, the person adds some amount of energy to the system. They add 50 newtons every meter at 5 meters. And then we know that the friction force will remove this at 5 meters as well. And then we know that this would equal our total work done. So this would be 1/2 mv1 squared, or v2 squared, minus 1/2 mv1 squared. So we could use this to solve for, say, what our frictional force is. If we know that velocity is constant, we know that 2 and 1 are the same, so this goes away, and we get that just the 50 newtons is equal to the frictional force. And this is what we expect if it's moving at a constant velocity. We know the net force on it needs to be 0 in order for it to move at a constant velocity. So instead, let's look at one where we're not talking about a constant velocity. Let's talk about one where we are rolling down a hill and we have some frictional force. So mu equals, let's say, 0.5. And I want to know that, well, let's say here it's moving at 5 meters per second. Down here it's moving at 10 meters per second. And the height difference is, let's say, 3 meters, right? So in 3 meters, it's gone 5 meters per second to 10 meters per second, and we have some friction. So let's see what our friction does. Well, we get the potential energy at the beginning plus the kinetic energy at the beginning, which would be 1/2 mv squared, is going to be equal to, because that's the types of energy we have at the beginning, right? We have mu g, and we have ek. So we have kinetic energy and potential energy at the beginning because it is moving. Then it's going to drop 3 meters, so we get that 1/2 mv final squared, and then we're going to add on our loss. The reason I add the loss here is because I know the total needs to be, related to the beginning, but it should be less for this one portion, so therefore this has to be added on. And all the energy should add up to be what we got at the beginning. If you want to think about it a different way, and you want your E loss to be how much has been taken away, you can always do mgh minus 1/2 mv squared, or plus 1/2 mv squared, minus the energy loss is equal to 1/2 mv final squared. They're the same thing mathematically, but conceptually one of them relates to your energy loss taking away from your initial energy that you had, and the other one relates to adding energy at the end such that you get the total amount of energy you had at the beginning. Either one is fine, it doesn't really matter. So now we're going to try and solve for our energy loss. And so I know that mgh, this will be mg3 plus 1/2 m, this is 5 squared, minus E loss is equal to 1/2 m10 squared. So then we get, let's see, mg, I didn't give myself enough numbers here, so let's say, what, mg3 plus, 25 over 2 m minus 1/2 100 over 2 m equals E loss. So then I'll get 30 m plus 25 over 2 is 12.5 m minus 50 m equals E loss. And then we get, this is going to be funny. All right, so then we would get 42.5 minus 50 m equals E loss. So actually we gained energy because our E loss, which we assumed to be negative, is negative 7.5. Right, so we actually gained 7.5 joules of energy. So let's say that this has a rocket booster on the back. There we go. So that was my fault for the numbers that I used. So let's do one that makes a lot of sense and just say that it's not moving initially at all at the beginning, because then it can't have done that really. So now we have this, which we're just going to give it a tiny little push, but we're not really going to increase its velocity at all. This is going to have a non-zero mu. They'll usually either give you the friction or you'll be solving for it. So here, if I say this is some height h, and then we want to find its velocity at the end to be able to find the amount of energy that we lost. So we do mgh minus the energy loss is equal to the energy at the end, which is all kinetic. So we get mgh minus E loss equals 1/2 mv squared. And then we can get that E loss is just equal to mgh minus 1/2 mv squared. And this makes a lot of sense because if you don't have any energy loss, these two things are equal, and therefore they cancel each other out. So that would show that you have no energy loss. So there you go. That makes a lot of sense. Ultimately, when solving energy problems, what we're going to do, so just how to solve. How to solve. Step 1, identify the energy at various locations, but they have to be important. This will usually be beginning and end. Right. Then step 2, set E start equal E end equal E at whatever point. Unless non-conservative forces exist. If non-conservative forces exist, then you do E start plus or minus energy loss slash add, and that would equal the energy at the end. So if something adds energy to your system, you would add it there. And if something takes away energy from your system, you would take it away there as a subtraction. You can also look at it as E start equal plus the work done on the system has to equal the energy at the end. Keep in mind that if work is done in the direction opposite the traveling distance, then this work done will be negative, and therefore that would be your energy loss. If it's in the same direction as your distance, then that would be positive work done, which would then add to your total energy at the end. Right? Step 3 is to replace U and E for all energies with their values. So UG goes to mg delta H, US goes to 1/2 kx squared for a linear spring, and EK, or the kinetic energy, goes to 1/2 mv squared. Then step 4, solve. All right, that's basically the whole unit. We covered, just to summarize real quick, we covered some sample problems. We went over the work energy theorem, where the work is equal to the change in kinetic energy, or the negative of the potential energy. The work is equal to force dot x, or F dot dx if you're in a calculus-based class, or the integral of F dot dx if you're in a calculus-based class. So that would be Fx cosine of theta. Likewise, if you're in a non-calculus-based class, right, and you're given a graph that's like F versus x, the answer is the area under the curve. This would be the work. So work done by that force would be the area under the curve if you're in a non-calculus-based class. Or if you're in calculus-based class, but that's just what the integral is, so you'd already know that. The power is work divided by time, so in this case it'll be, kinetic energy over time, or the change in kinetic energy over time. Keep in mind that the power times the time gives you the work. This is probably the one that you will use the most. Power times time equals work. The kinetic energy is 1/2 mv squared. The potential energy due to gravity is mgh, or really mg delta h, but you can always define the lowest height in your problem to be 0, and then relate it to that lowest height, so that it's just equal to h. And then the energy from a spring, or the potential energy from a spring, if it's a linear spring, is 1/2 kx squared. If you're in a calculus-based class, they might make you do stuff with nonlinear springs. If you're in an algebra-based class, they will never do that. So that's useful, just because you can't find it. In that case, if they ever did do something like that, they would give you what the potential energy for that spring looked like as a function of x. In order to solve these problems, we do a bunch of them here as sample problems and then go over energy loss and energy adding, right? So really you would identify the energy at various important spots. So if we look back up here at the top, we identified at the beginning, we have gravitational potential energy because we are above 0. At the end, we have only spring because the spring is collapsed. And then, you know, when we have non-zero friction, we can do that because we have no conservative force, or we have no non-conservative forces. If we ever have non-conservative forces, we have to account for the loss or addition of energy, which is the work done on that system. So if you have a conservative force, then effectively no work is done to change the amount of energy in the system, right? So any work that is done by a force such as gravity or whatever, we'll be able to give that work back later. Then we replace the energy, you know, the EK and U and all that stuff with their correct equations. So UG is mg delta H, US is 1/2 kx squared, and EK is 1/2 mv squared. Then we solve for whatever value we need. Now, identifying types of energy is useful. So how to identify? All right. So let's talk about 3 questions we can ask ourselves. All right. The first question is it moving? If yes, we have kinetic energy. Two, is it above 0? So if we call the lowest point in our problem 0, is it above that point? If yes, then you have U sub g, which is gravitational energy, which is mgh. This is 1/2 mv squared up here for kinetic energy. All right, number 3. Is a spring doing anything? Well, if yes, we have US, which is 1/2 kx squared, and this is spring potential. All right, so if we want to look at our problem that involves all of these, I guess there is a 4th one. 4, is energy lost or added? If yes, then you do E start plus the work done equals E end. And remember that can be positive or negative. All right, so now let's look at a problem that we did earlier, and I'll show you exactly how I thought about this one. All right, so we have block up here at some height. And then it's going to fall down this ramp and then hit this thing, and we're going to call this elastic. Because if we don't, then we have to use momentum, and we don't know how to do that yet. Okay, so at the beginning, I'm going to look at 3 points. I'm going to look at the beginning, say right here, and once it completely compresses the spring. Right, so 3 basic points. Up here, I have mgh. Right here, I have 1/2 mv squared if we assume this is at its lowest point. And right here I have 1/2 kx squared. So questions they could ask, would be, how fast is it going when it hits the spring? Well, that would be mgh is equal to 1/2 mv squared, if I assume no energy loss. They didn't mention any energy loss, so I'm going to assume that energy is not lost, and this is a conservative system. So that's something they could do, and then in that case you just cancel out the m's and you get v equals square root 2gh. All right, perfect. Now, let's say the spring compresses, let's say x equals 1/4 expectation. How much energy is lost in the spring collision? So now our assumption is no longer correct that this is elastic. That would be our expectation. So now our system is not conserving energy. So we know that we have mgh at the beginning, and this is going to equal 1/2 kx squared, right? And I know mgh minus 1/2 k 3/4 of x squared is going to be the energy that was lost, and this will equal 1/2 k 1/4 x squared. And this is actually what they're looking for right here. So you see how if I added this back over here, I would get the total x, right? But I know that this is actually something that I lost. So that's what they're looking for. So yeah, so this would actually be 9/16 of 1/2 kx squared, and I know that 1/2 kx squared is mgh. So this would be 9/16 of mgh, so 9/16 of the total energy is lost. Right. So we know that it compressed only 1/4 of expectation, which means that it was not compressed by 3/4. So the energy that would relate to it being compressed 3/4 of the way was actually lost. And we can find that out from this. So there we go. And then it ended up being 9/16 because of the square. So hopefully this shows you quite a bit about what you can do with energy problems and how much easier they are than forces problems. Simply identifying the energy is really much easier than trying to draw force diagrams and doing all these other things. Trying to draw a force diagram for something on a curved slope, so something like this, is abysmal, but using energy, as long as you know the height, you can find the velocity at the end. Okay, that's all of energy for the most part. Cool. If you have any questions, let me know. Thanks.